There's a moment just before the sun unleashes its fury, when the silence of space is shattered by something unimaginable. A colossal eruption bursts from the sun's surface, a torrent of energy so vast it could power our planet for centuries. This is a solar flare, one of the most violent and mysterious phenomena in our solar system. In mere seconds, temperatures soar to millions of degrees, magnetic fields twist into impossible shapes, and radiation floods the cosmos. And yet, despite decades of study, these explosions still hold secrets that defy explanation. What if I told you that some of these solar flares behave in ways that shouldn't be possible, that they leave behind anomalies so baffling, even the brightest minds in astrophysics can't fully unravel them? From flares that vanish without a trace to bursts of energy that shouldn't exist according to our laws of physics, the sun is hiding puzzles no one saw coming. And today, we're diving deep into 30 of these unexplained phenomena, each one a reminder that the universe loves to keep us guessing. Think about it, the sun is the one constant in our lives, the steady heartbeat of our solar system. But beneath its familiar glow lies a storm of chaos and mystery. Some flares trigger blackouts on Earth, while others dance with auroras in ways we can't predict. Some even seem to communicate, or at least that's what the data suggests. What's really happening out there? What forces are at play that we haven't even begun to understand? Buckle up, because we're about to journey into the heart of these solar enigmas, where every discovery raises more questions than answers. The sun has been keeping secrets, and it's time we uncover them. The night sky erupted in color like never before on September 1st, 1859. Auroras danced as far south as Cuba and Hawaii, so vivid that miners in the Rocky Mountains woke up thinking it was dawn. Telegraph systems across Europe and North America failed. Some operators reported sparks leaping from their equipment, even fires breaking out. This was the Carrington Event, the most powerful solar storm ever documented. And here's the unsettling truth. Over a century and a half later, we still don't know when or if another flare like it will strike again. What made the Carrington Event so extraordinary wasn't just its raw power, but the sheer unpredictability of its arrival. Astronomer Richard Carrington witnessed the initial burst through his telescope, a blinding white light erupting from a sunspot cluster. But here's the mystery: the sunspots themselves weren't unusually large. Modern reconstructions suggest this wasn't a once-in-a-millennium event either. Statistically, flares of this magnitude should happen every few hundred years. Yet, in the years since, nothing has come close. That discrepancy haunts scientists today. The consequences of a repeat performance would be catastrophic on a scale we're only beginning to grasp. In 1859, the world relied on telegraph wires. Today, our entire civilization is threaded with vulnerable technology. A Carrington-level flare could fry satellites, cripple power grids for months, and disrupt GPS systems that govern everything from air travel to financial transactions. In 2012, we narrowly missed a storm of similar magnitude. It passed through Earth's orbit just days after our planet had moved out of harm's way. So why can't we predict the next one? The sun's behavior remains frustratingly opaque. Some theories suggest these megaflares require a perfect and rare alignment of twisted magnetic fields, like a cosmic lightning bolt waiting for just the right conditions. Others argue we might be misreading the sun's activity cycles entirely, missing hidden patterns in the chaos. One thing's certain: until we solve this puzzle, we're at the mercy of a star that's proven it can catch us off guard. The Carrington Event wasn't an anomaly, it was a warning, and the clock is ticking on when the sun decides to send the next one. Scientists have spent decades simulating solar flares, feeding data into supercomputers to predict how much energy these explosions should release. But again and again, reality defies the models. Some flares erupt with a whimper instead of a bang, their actual energy output falling shockingly short of theoretical calculations. This discrepancy is called the missing energy problem, and it points to giant gaps in our understanding of solar physics. Where does all that predicted energy go? One leading theory suggests solar flares might be funneling huge amounts of power into invisible channels, perhaps as subtle plasma waves or particle acceleration we can't yet detect from Earth. It's like watching a bonfire from a distance and only seeing half the flames. The rest could be radiating in wavelengths our instruments aren't designed to catch. Another possibility cuts even deeper. Maybe we're fundamentally wrong about magnetic reconnection, the process long thought to power these eruptions. Magnetic reconnection happens when tangled solar magnetic fields snap and rejoin, a phenomenon often compared to rubber bands breaking and fusing back together. This should unleash torrents of energy, but something about the math doesn't add up. Recent observations from NASA's Parker Solar Probe hint that reconnection might be far messier than our clean laboratory models suggest, with energy dissipating in ways we haven't accounted for. The stakes here are higher than academic curiosity. If we're underestimating where flare energy goes, we could be blindsided by its side effects. That missing energy might be fueling stealthy radiation bursts or lingering shockwaves capable of damaging satellites over time. Solving this puzzle isn't just about rewriting textbooks, it's about protecting our technology-dependent world from hazards we don't yet see coming, perhaps the most humbling possibility. The sun might be operating by rules we haven't discovered yet. While physicists tweak equations and launch new probes, our closest star keeps its secrets, releasing flares that behave like riddles written in fire. Until we crack this code, every solar explosion comes with an invisible question mark. Just when we thought solar flares couldn't get any stranger, scientists stumbled upon something that shouldn't exist: plasma rivers barreling into the sun at speeds faster than sound. Picture this: during a flare's explosive chaos, while most material is hurled outward in a fiery tempest, some of it reverses course like a cosmic boomerang, plunging back toward the sun's surface at over 1,000,000 miles per hour. These are supersonic downflows, and they've left physicists scratching their heads for years. Here's why this breaks the rules. Solar flares are powered by magnetic reconnection, a process where twisted magnetic fields snap and release energy, catapulting plasma away from the sun. Think of it like a slingshot. Once the tension is released, everything should fly outward, but downflows turn that logic upside down. It's as if you fired a cannonball, only to watch it suddenly U-turn midair and slam back into the barrel. Even stranger, these downflows aren't rare quirks. They're detected in nearly half of all observed flares. So why does the sun's fury sometimes suck matter back in? One theory suggests these flows might be the solar equivalent of a shockwave rebound. When the initial explosion slams into surrounding plasma, it could create a violent backflow, like ocean waves crashing back after hitting a cliff. Another idea points to magnetic bottle effects, regions where the sun's tangled fields might trap and redirect plasma inward at insane speeds. But neither explanation fully accounts for the sheer velocity or the way these downflows sometimes appear before the flare's peak, almost as if they're part of the trigger rather than a consequence. The implications are staggering. If downflows play a role in how flares ignite or evolve, our entire understanding of these explosions might be missing a critical piece. Some researchers speculate these supersonic rivers could even act as energy channels, siphoning power back into the sun's depths and fueling subsequent eruptions. It's a cosmic feedback loop we never saw coming. What's clear is that the sun's drama doesn't follow a simple script. With every flare, it serves up reminders that the universe's rulebook has pages we haven't even opened yet. And until we crack the code of these supersonic mysteries, we're left watching in awe as the sun defies physics right before our eyes. Some solar flares play tricks on our instruments, erupting with a burst of high-energy X-rays while leaving almost no trace in visible light. These are dark flares, a paradox that defies everything we know about how energy should radiate from the sun's explosions. Normally, a flare's fury lights up across the electromagnetic spectrum from radio waves to gamma rays. But dark flares, they're like ghosts, felt but not seen, their X-ray signatures blazing while the sun's surface remains eerily unchanged. The mystery lies in the energy mismatch. X-rays come from electrons accelerated to nearly the speed of light, a process that should also generate intense visible light as those electrons slam into the sun's dense lower atmosphere. Yet in dark flares, that visible component is suspiciously absent. It's as if someone turned off the lights but left the furnace roaring. Recent observations from Japan's Hinode satellite and NASA, a solar dynamics observatory, have catalogued dozens of these events, each one deepening the puzzle. Scientists are chasing two leading theories. The first suggests these flares might be happening deeper in the sun's atmosphere than usual, where the plasma is so dense that visible light gets absorbed before it can escape. Imagine a flashlight submerged in murky water. The beam might not reach the surface even if the bulb is blazing. The second theory is more radical. Dark flares could involve a rare form of particle acceleration that skips the usual steps, funneling energy directly into X-rays while bypassing visible emissions entirely. But here's where it gets even weirder. Some dark flares coincide with another unexplained phenomenon, stealth coronal mass ejections, where massive clouds of plasma leave the sun with no apparent trigger. Could these shadowy eruptions be linked? The possibility hints at a hidden layer of solar activity, a realm of energy transfer we're only beginning to glimpse. The stakes go beyond curiosity. X-rays from solar flares can ionize Earth's upper atmosphere, disrupting radio communications and GPS signals. If we're underestimating how often these invisible flares occur, our space weather forecasts might be missing a silent threat. Every dark flare is a reminder. The sun's playbook holds chapters we haven't read, written in wavelengths we're still learning to see. Gamma rays, the most energetic light in the universe, usually come from the most violent cosmic events, colliding neutron stars, exploding supernova, the voracious mouths of black holes. But here's the twist. Our relatively calm sun occasionally fires off gamma ray bursts too, and we still can't fully explain how. These aren't just faint whispers of gamma radiation. Some solar flares produce enough to light up detectors like a cosmic flashbang. The puzzle isn't just that it happens, but how, because the sun shouldn't have the power to accelerate particles to the near-light speeds required. At the heart of the mystery is a process scientists call particle acceleration on steroids. Normally, solar flares energize electrons and protons through magnetic reconnection, those snapping and twisting fields we've talked about. But to produce gamma rays, particles need to reach energies 1,000 times higher than standard flare physics predicts. It's like a slingshot suddenly launching a pebble at bullet speed. So where's the extra kick coming from? One clue comes from a peculiar pattern. The strongest gamma ray flares often coincide with shocks in the sun's atmosphere, where plasma waves crash into each other at supersonic speeds. Picture oceanic tidal waves, but made of superheated gas, colliding with enough force to catapult particles to insane velocities. There's also mounting evidence that the sun's magnetic fields might act like cosmic particle accelerators, far more efficient ones than we'd imagined. In certain configurations, these fields could whip particles back and forth like a ping-pong ball in a tornado, gradually ramping up their energy until they smash into surrounding matter, sparking gamma-ray fireworks. Yet even these explanations hit a snag. Some gamma-ray flares emit light with a bizarre double peak, two distinct bursts separated by minutes or hours. That suggests two separate acceleration events happening in the same flare, a behavior no current model predicts. Even stranger, a handful of these gamma rays appear to come from behind the sun, as if particles are being hurled around its horizon like a boomerang. The implications ripple far beyond solar physics. If the Sun, a relatively tame star, can generate such extreme particle energies, what does that mean for more violent stars elsewhere in the galaxy? Could similar mechanisms be hiding in plain sight, masquerading as ordinary flares while secretly producing radiation capable of stripping atmospheres from planets? Every unexplained gamma ray burst from our Sun is a reminder. Even the most familiar cosmic objects can harbor the universe's best-kept secrets. And until we solve this puzzle, we're left staring at a star that occasionally winks at us with light that shouldn't exist. Most solar flares follow a predictable life cycle of violent eruption, a peak of intensity, then a gradual fade into silence, but some refuse to play by those rules. These are zombie flares, eruptions that vanish only to roar back to life hours or even days later, like a fire repeatedly rekindling itself from its own ashes. The first confirmed case appeared in July 2012, when a flare over the Sun's western limb dimmed after its initial outburst, only to surge back with unexpected fury nearly 60 hours later. Since then, solar physicists have catalogued dozens of these undead eruptions, each one challenging our understanding of how magnetic energy dissipates in the Sun's atmosphere. What makes these flares so baffling isn't just their persistence, but their defiance of decay models. Normally, a flare's decline should mirror the unraveling of its magnetic fields, like a snapped rubber band losing tension as it settles. Zombie flares, however, suggest the Sun's magnetic fields might be far more resilient than we thought, storing and releasing energy in pulses rather than all at once. High-resolution imagery from the Solar Dynamics Observatory reveals something eerie. These flares often reignite in the exact same location, as if some hidden structure beneath the Sun's surface keeps reloading the gun. The leading suspect, so-called magnetic flux ropes, twisted bundles of magnetic field lines that coil like springs beneath the Sun's surface. Imagine a jack in the box where the lid keeps slamming shut before the clown fully pops out. In zombie flares, these ropes might partially release their energy, then snap back into place, only to unleash another burst when surrounding plasma conditions shift. Some simulations even suggest these ropes could intertwine with neighboring fields, creating a network of energy reservoirs that feed the flare in waves. But there's a darker possibility. Zombie flares might be evidence of a fundamental flaw in how we model magnetic reconnection, the process thought to power all solar eruptions. Traditional models assume reconnection is a one-time event, like a single match igniting a bonfire. What if it's more like a gas stove, capable of flaring up repeatedly as fresh fuel trickles in? If true, our entire framework for predicting flare intensity and duration might need rewriting. The stakes here aren't just academic. A zombie flare's prolonged activity could expose Earth to extended radiation storms, battering satellites over multiple rotations of the Sun. Worse yet, these flares often coincide with stealth coronal mass ejections, those sneaky plasma clouds we discussed earlier, raising the terrifying prospect of a double punch, a hidden ejection followed by a resurrected flare. As probes like Parker Solar Probe dive closer to the Sun than ever before, they're hunting for clues in the plasma currents and magnetic whispers around these undead eruptions. Every zombie flare is a reminder the Sun doesn't just explode its schemes, and until we crack its magnetic playbook, we're left watching the skies for flares that refuse to stay dead. The Sun's corona already defies logic, hovering at millions of degrees while the surface below simmers at a comparatively chilly 6,000. But during solar flares, certain pockets of plasma scream past even those staggering numbers, hitting temperatures that make the corona seem tepid. We're talking localized infernos reaching tens of millions of degrees hotter than the cores of some stars. What's bizarre isn't just the heat, but the precision of these thermal spikes. Like cosmic blowtorches, they sear through narrow regions of a flare while adjacent zones remain relatively cool. This isn't just an extreme phenomenon, it's a violation of everything we know about how energy distributes in space. At the heart of the mystery lies a fundamental question. How can such extreme temperatures arise so fast? Flares don't gradually warm up, they spike in seconds as if someone flicked a celestial switch. Standard heating mechanisms like magnetic reconnection can't fully account for these blistering numbers. It's like trying to explain a forest fire with the heat from a matchstick. One leading theory points to nanoflares, countless tiny explosions too small for our telescopes to detect individually, but whose combined energy might superheat localized plasma. Think of it as a microwave with 1,000 invisible hotspots, each one contributing to a scorching whole. Yet even nanoflares don't solve the puzzle entirely. Observations from the European Space Agency's solar orbiter reveal another wrinkle. These ultra-hot zones often form along magnetic field lines rather than at reconnection sites. That suggests an unknown acceleration process might be at work, perhaps one where particles surf on plasma waves to unimaginable energies. There's also the odd coincidence that these temperature spikes frequently align with gamma-ray emission zones, hinting that particle collisions at near-light speeds could be dumping energy into the plasma like a cosmic game of bumper cars. The implications shake the foundations of plasma physics. If we're missing a key heating mechanism on our own sun, what does that mean for understanding more violent stars across the galaxy? Worse yet, these thermal anomalies could be stealthily amplifying space weather risks. Hotter flares mean more intense X-rays and energetic particles, the kind that can punch through satellite shielding or distort Earth's upper atmosphere. Some researchers are now questioning whether we've misjudged the sun's energy budget entirely. Could these fleeting infernos hold clues to a larger, hidden system of energy transfer? Until we solve this thermal riddle, every solar flare carries a dual signature: the light we can see and the invisible, inexplicable heat we're only beginning to measure. The sun isn't just burning, it's holding masterclasses in extremes we're struggling to decode. When solar flares erupt, we expect chaos, a violent spray of plasma and radiation bursting outward in all directions. But some flares refuse to follow this messy script. Instead, they twist themselves into elegant spirals, coiling like cosmic corkscrews as they tear through the sun's atmosphere. These helical flares are more than just a stunning spectacle. They're a direct challenge to everything we thought we knew about solar magnetism. The mystery lies in their precision. Simple magnetic loops, the classic model for flare structures, should snap outward in relatively straight lines when they reconnect. But corkscrew flares form near-perfect helices, sometimes completing multiple full rotations before dissipating. It's like watching a lightning bolt curl into a spring instead of zigzagging randomly. High-resolution images from NAS, a solar dynamics observatory, reveal these structures in shocking detail, with plasma threads winding around an invisible axis like strands of a DNA molecule. So what's bending these eruptions into such unnatural shapes? One theory points to a hidden ingredient: magnetic turbulence. The sun's magnetic fields might not just be orderly loops but tangled vortices spinning beneath the surface, like submerged whirlpools waiting to erupt. When these twisted fields finally snap, they could drag the escaping plasma into a rotational dance. Another possibility involves the plasma itself. Certain configurations might trigger instabilities that cause the flare to kink as it rises, like a garden hose writhing under too much pressure. But here's where things get stranger. Some corkscrew flares exhibit behavior that defies even these explanations. A few have been observed rotating in the opposite direction of the sun's natural spin, as if some unseen force is overriding the star's dominant motion. Others show variable pitch, starting as tight coils before suddenly loosening, like a spring being stretched mid-flight. These anomalies hint at forces we haven't yet accounted for, possibly tied to deeper layers of the sun's dynamo. The implications reach far beyond aesthetics. Helical flares might be funneling energy more efficiently than their straight counterparts, like a rifle barrel imparting spin to a bullet. This could explain some of the extreme particle accelerations we see in gamma-ray flares. Worse yet, their twisted structure might make them more likely to trigger coronal mass ejections, those planet-threatening plasma storms. If we're underestimating how often these spirals form, our space weather forecasts could be missing a critical variable. For now, corkscrew flares remain one of the sun's most mesmerizing contradictions, a blend of chaos and geometry that refuses to fit neatly into our models. Every new observation raises the same unsettling question. If we're still surprised by the sun's simplest shapes, how much more complexity are we missing? One of the most astonishing feats of a solar flare isn't just its raw power, it's the way it turns the sun's atmosphere into a cosmic particle accelerator, hurling electrons and protons to velocities approaching the speed of light. These aren't gentle nudges, they're violent slingshots that launch particles with energies surpassing the most advanced human-made colliders. Yet despite observing this phenomenon for decades, physicists still grapple with a fundamental question. How does the sun achieve this so effortlessly, while our best technology requires kilometers-long tunnels and megawatts of power to even come close? The puzzle begins with the numbers. During major flares, particles can reach energies up to tens of giga-electronvolts, comparable to some cosmic rays from distant galaxies. That's like a pebble being tossed with the force of a cannonball. Traditional models point to magnetic reconnection as the primary engine, where tangled fields snap and realign, creating electric fields that catapult particles outward. But here's the catch: standard reconnection alone can't explain the efficiency of this acceleration. Particles in flares gain energy hundreds of times faster than laboratory experiments or simulations predict, as if the sun has a hidden turbocharger we haven't accounted for. Recent observations have added layers to this enigma. High-resolution data from the Parker Solar Probe reveals something unexpected. Particles often emerge from flares with a broken power law distribution, a fancy term meaning their energies cluster in specific, uneven tiers rather than a smooth spectrum. This suggests multiple acceleration mechanisms might be working in tandem, like a cosmic assembly line where particles get sequential boosts. Some theories propose that shock waves rippling through the flare's plasma act like successive speed bumps, each one kicking particles faster. Others point to contracting magnetic islands, pockets of twisted fields that collapse violently, squeezing trapped particles to extreme energies like grapes in a vise. Then there's the location mystery. Contrary to expectations, the most energetic particles don't always originate at the flare's core. Some seem to gain their speed far from the reconnection site, as if the acceleration process is somehow distributed across the entire eruption. This has led to radical ideas like turbulent acceleration, where chaotic plasma waves, think ocean surf but made of magnetized gas, batter particles to high speeds through countless microscopic collisions. It's a messy, stochastic process that mirrors how cosmic rays get boosted in supernova remnants, just on a much smaller scale. The stakes of solving this riddle stretch far beyond solar physics. If we can decode the sun's particle acceleration secrets, we might unlock new ways to replicate the process here on Earth, potentially revolutionizing everything from medical radiation therapy to fusion energy. But more urgently, these high-energy particles pose a direct threat to astronauts and satellites, capable of penetrating shielding and frying electronics. Right now, our inability to predict their intensity leaves critical infrastructure vulnerable. Perhaps the most humbling realization is that our nearest star may be operating by rules we haven't yet written. Every flare's particle outburst is a reminder. In the face of nature's genius, even our most advanced science is still playing catch-up. The sun isn't just a ball of plasma, it's the universe's most efficient particle accelerator, and its blueprint remains just out of reach. Solar flares aren't supposed to appear out of nowhere, at least that's what we thought. For decades, the rule was simple. Flares erupt from active regions, those chaotic tangles of magnetic fields marked by dark sunspots. But the sun has a habit of breaking its own rules. Enter the quiet sun, flares mysterious eruptions that burst forth from seemingly placid, spotless regions of the solar surface, defying every textbook explanation. These flares shouldn't exist. Without sunspots, there's no obvious tangle of magnetic energy to fuel an explosion. Yet satellite data doesn't lie. In 2008, the Hinode spacecraft caught one of these events in the act, a full-fledged flare erupting from a patch of the sun as featureless as a calm sea. Since then, astronomers have documented dozens more, some even reaching mid-tier intensities. The question isn't just how they happen, but where the energy comes from in the first place. One possibility cuts to the core of how we understand the sun's magnetism. Hidden beneath the visible surface, magnetic fields might be weaving themselves into knots too subtle for our telescopes to detect, like invisible fault lines building pressure until they snap. Some researchers call these ghost fields, strands of magnetism that don't manifest as sunspots but still store enough energy to ignite a flare. Think of it as a stealthy solar underground operating just beyond our sight. Another theory takes the mystery deeper literally. Simulations suggest that quiet sun flares could be tapping into the sun's global magnetic field, the vast, diffuse network that stretches far beyond active regions. If certain configurations of this field pierce through the surface in just the right way, they might trigger localized explosions without leaving the usual sunspot calling card. It's like lighting a match in a room full of unseen gas. No one notices until the flame bursts to life. The implications rewrite what we know about solar risk. If flares can strike without sunspots, our early warning systems, which rely heavily on monitoring active regions, might be missing silent threats. A quiet sun flare directed at Earth could catch us completely off guard, potentially skirting space where the forecasts meant to protect satellites and power grids. Perhaps the most unsettling aspect, these flares hint that the sun's magnetic personality is far more complex than we've assumed. What looks like a blank canvas to our instruments might be a hidden labyrinth of energy waiting for the right moment to reveal itself. Every quiet sun flare is a whispered challenge. You don't know me as well as you think, and until we decode this enigma, we're left watching the sun's calmest patches with a new sense of unease. There's an eerie silence that follows some solar flares until suddenly the sun starts screaming, minutes or even hours after the initial eruption. While the visible fury has faded, colossal bursts of radio waves explode from the same region. These delayed radio bursts shouldn't happen, at least not according to our current models of flare physics. If the main explosion is over, where is all this late arriving energy coming from? The mystery lies in the timing. Radio emissions from flares typically coincide with the initial outburst, generated by electrons spiraling along magnetic field lines like cosmic antennas. But delayed bursts break that rhythm entirely. Observations from radio telescopes like the Carl G. Jansky Very Large Array have clocked these post-flare signals at staggering intensities, some packing more energy than the original flare's radio output. It's as if a thunderclap echoed back long after the lightning strike. Except in this case, the echo is louder than the initial blast. One clue comes from the burst structure. Many exhibit a distinctive, drifting pattern where frequencies shift gradually over time. This suggests particles are accelerating through progressively weaker magnetic fields, like a ball rolling down a cosmic hill, picking up speed as gravity lessens. The problem, those fields should have relaxed back to normal long before the delay ends. Some theorists argue this points to post-flare reconnection, where the sun's magnetic fields continue snapping and reforming behind the scenes, quietly reloading energy reserves like a celestial battery. But there's a wilder possibility. Delayed bursts might trace their origins to shock waves plowing through the sun's outer atmosphere long after the flare's peak. Imagine tossing a rock into a pond. The initial splash is the flare, but the ripples hitting distant shores could be these radio outbursts. As these shocks travel, they might encounter dense plasma pockets or tangled magnetic threads, creating secondary electron accelerations that light up radio telescopes unexpectedly. The implications ripple beyond curiosity. Radio bursts can interfere with GPS and aviation navigation systems, meaning a flare we think has passed might still harbor hidden threats. Worse yet, if delayed emissions correlate with stealth coronal mass ejections, we could be missing crucial warning signs for space weather hazards. Every unexplained radio burst is a reminder. The sun's explosions aren't one-act plays, but complex dramas with encores we're only beginning to hear. The sun is supposed to be the ultimate independent operator, a solitary sphere where one region's chaos shouldn't influence another's. But solar flares have a strange habit of defying isolation. Across the sun's vast surface, eruptions sometimes occur in near-perfect sync, separated by hundreds of thousands of miles, yet bound by something invisible. These are sympathetic flares, and their existence suggests a hidden network of magnetic connections threading through the solar atmosphere like cosmic puppet strings. Take what happened on August 1, 2010. Over just 36 hours, a chain reaction of flares erupted across the sun's western hemisphere, not in a single active region, but in 4 distinct zones spread wider than the distance between Earth and the Moon. At first glance, these areas appeared completely unrelated, yet their explosions were too perfectly timed to be coincidence. Data from NAS, a solar dynamics observatory, revealed something even stranger. Loops of ultraviolet plasma began bridging the gaps between these regions before the flares started, as if tracing invisible highways in the sun's atmosphere. The leading theory points to large-scale magnetic coupling, where disturbances in one part of the sun's magnetic field propagate across vast distances, triggering instabilities elsewhere. Imagine plucking a single thread in a spiderweb. The vibration travels far beyond the initial touch. In the sun's case, these threads might be magnetic flux tubes, structures theoretically linking different layers of the solar atmosphere. When one tube snaps during a flare, the shockwave could ripple through others, setting off secondary explosions in regions that should be magnetically insulated. But there's a problem: the speeds don't add up. Magnetic disturbances should travel as Alfvén waves, ripples moving at the pace of the local magnetic field. To connect flares hundreds of thousands of miles apart within minutes, these waves would need to move faster than the sun's physics should allow. Some researchers speculate the coupling might involve a more exotic mechanism, like fast mode shocks that race through the corona at inexplicable velocities. Others wonder if the sun's global magnetic field acts as a silent conductor, orchestrating eruptions like a cosmic symphony. The implications are staggering. If sympathetic flares are more common than we realize, our space weather forecasts might be missing a critical domino effect. A moderate flare in one region could secretly prime another for catastrophe, turning what seemed like isolated events into a cascading threat. Worse yet, this phenomenon might explain historical superstorms, where multiple eruptions struck Earth in quick succession, events we've long assumed were random coincidences. Perhaps the most profound revelation, the sun's surface, which appears fragmented and chaotic to our telescopes, might be laced with an invisible architecture, a web of connections we're only beginning to trace. Every sympathetic flare is a clue, whispering that the sun's greatest secrets don't lie in its explosions, but in the spaces between them. Here's a paradox that rewrites the rules of solar physics: flares that unleash unfathomable energy while leaving pockets of plasma suspiciously, unnervingly cold. These so-called cold flares should be impossible, like a forest fire that somehow leaves patches of frost in its wake. While most of a flare's plasma roars to millions of degrees, these anomalous zones stubbornly linger at temperatures barely warmer than the sun's quiet surface, defying every expectation of how energy should distribute during an explosion. The mystery isn't just academic, it strikes at the heart of how we model stellar heating. Standard flare physics dictates that magnetic reconnection, the snapping and realigning of twisted fields, should superheat surrounding plasma like a blast furnace. Yet in cold flares, something interrupts this process, creating thermal voids where the heat seemingly vanishes. Observations from the IRIS satellite reveal these cold patches with eerie clarity, regions where ultraviolet emissions, typically a telltale sign of scorching plasma, drop to near background levels as if shielded by an invisible barrier. One leading theory suggests these cold zones might be magnetic shadows, areas where flare energy gets redirected rather than absorbed. Picture water flowing around a boulder in a stream. The plasma might be channeled away from certain pockets by stubborn magnetic geometries that refuse to reconnect. Another idea points to rapid cooling mechanisms, where dense plasma blobs sink and dissipate heat faster than the flare can replenish it, like ice cubes dropped into a boiling pot. But the most tantalizing possibility, these cold flares might be exposing gaps in our understanding of energy transfer at quantum scales. Some astrophysicists speculate that certain magnetic configurations could trigger anomalous cooling effects, akin to how superconductors expel magnetic fields. If true, the Sun could be hiding laboratory-scale physics operating on a stellar stage, a phenomenon we've never witnessed elsewhere in nature. The stakes are higher than theoretical curiosity. Cold flares might be the missing link in explaining why some eruptions fail to produce expected coronal mass ejections, or why radiation signatures sometimes deviate from predictions. Every unexplained thermal void is a silent reminder. The Sun's energy dance is far more intricate than our models can yet describe, and until we crack this paradox, our forecasts of space weather's most violent acts will remain incomplete. The Sun isn't just hot or cold, it's both at once, laughing in the face of our neatly categorized physics. Solar flares should be neutrino factories. When atomic nuclei get torn apart in these explosions, the nuclear reactions should release a torrent of ghostly particles called neutrinos, billions streaming through every square inch of space. That's the theory, but reality has played a cruel joke on physicists. Despite decades of watching flares with neutrino detectors buried deep underground, the expected flood of particles never arrives. It's as if the Sun's most violent explosions are somehow hiding their nuclear secrets in plain sight. This missing neutrino problem cuts to the core of how we understand solar energy. Neutrinos are born in nuclear processes, specifically when protons fuse or heavier elements break apart. During flares, the sheer violence should ramp up these reactions exponentially. Yet observatories like Japan's Super Kamiokande, capable of catching neutrinos from supernova halfway across the universe, report only eerie silence when a flare erupts. Even the monster X-class flares barely nudge the detectors. The discrepancy isn't just a minor gap, it's a canyon between prediction and observation. One explanation could rewrite solar physics entirely. Maybe flares don't get their energy from nuclear reactions at all. Instead of atomic nuclei fueling the explosions, the power might come purely from magnetic processes, twisted fields snapping and releasing stored energy like cosmic rubber bands. This would explain the neutrino absence, but raise another troubling question. If flares are purely magnetic, why do their X-ray signatures so perfectly mimic nuclear reactions? The light we see looks exactly like what proton collisions should produce, right down to the spectral lines. There's a wilder possibility. Neutrinos might be escaping detection because they're not the ordinary kind we're used to. The Sun primarily produces electron neutrinos, but if flares somehow generate sterile neutrinos, a hypothetical, nearly undetectable variant, our current instruments would miss them entirely. This would imply flares are tapping into exotic physics beyond the standard model, a notion both thrilling and terrifying for particle physicists. The stakes here transcend solar science. If we're wrong about how flares generate energy, our entire understanding of stellar processes from the Sun to distant supernova might need revisiting. Every neutrino detector trained on the sun is now hunting for these ghosts, waiting for the one flare that finally breaks the silence. Until then, the sun's explosions remain a nuclear riddle wrapped in a magnetic mystery. Most solar flares are over in minutes, violent bursts of energy that flash and fade like cosmic fireworks, but some refuse to follow the script. These are ultra-long duration flares, eruptions that stretch for hours, sometimes even days, lingering like a stubborn ember in the sun's atmosphere. The record holder, a monstrous flare in 2003 that crackled for nearly 36 hours, an eternity by solar standards. These marathon eruptions aren't just curiosities, they're red flags hinting that the sun's energy storage operates on scales we've barely begun to comprehend. What makes these flares so baffling is the sheer stamina they exhibit. Typical flares exhaust themselves once their magnetic fuel. The twisted field lines snap and release pent-up energy. But ultra-long flares suggest the sun has hidden reservoirs, ways to siphon energy into an eruption over prolonged periods. Imagine trying to light a bonfire with a single match, only to watch it burn for days without adding more wood. That's the kind of mystery physicists are grappling with. One clue lies in the flare's structure. Observations from the European Space Agency's solar orbiter reveal that many long-duration flares aren't single explosions, but chains of smaller bursts strung together. It's as if the initial eruption unlocks a valve, allowing energy to leak out in pulses rather than all at once. Some researchers compare it to a series of dominoes falling in slow motion, each one triggering the next but with agonizing delays between them. The question is, what's controlling that valve? The leading suspect is a phenomenon called magnetic flux feeding, where fresh magnetic fields slowly emerge from the sun's interior to replenish the flare's energy. Think of it like a gas stove where someone keeps turning up the flame incrementally. High-resolution magnetograms, maps of the sun's magnetic field, show something eerie during these events. New magnetic threads surfacing during the flare, as if the sun's dynamo is actively refueling the explosion from below. Yet even this explanation falls short for the most extreme cases. Some ultra-long flares exhibit energy outputs that exceed what their visible magnetic structures should hold, implying a form of storage we can't yet image. There's speculation that the sun's deeper layers, the convection zone, might act like a hidden battery, stockpiling energy far beneath the surface before releasing it in drawn-out trickles. The implications are urgent. Long-duration flares often coincide with the most dangerous coronal mass ejections, those planet-sized plasma clouds that can fry satellites and knock out power grids. Worse yet, their extended timelines mean Earth could sit in a storm's crosshairs for days, bombarded by radiation in waves rather than a single punch. Current space weather models struggle to predict these events precisely because we don't understand how the sun sustains them. Every ultra-long flare is a cosmic lesson in humility. The sun isn't just storing energy, it's doing so in ways that defy our best instruments and theories. And until we crack this code, we're left watching the clock, wondering when the next slow-burning eruption will remind us how much we still have to learn. Some solar flares announce their presence with blinding X-rays and swirling plasma, impossible to miss. Others operate like cosmic ghosts, completely invisible to our telescopes until they slam into Earth's atmosphere with unmistakable force. These are ionospheric flares, eruptions so stealthy they leave no trace on the sun's surface yet trigger dramatic disturbances in our planet's upper layers. The first definitive case emerged in 2006 when sensors detected a sudden spike in ionospheric ionization, the telltale fingerprint of a solar flare, yet every satellite trained on the sun came up empty. No burst of light, no surge of radiation, just Earth's atmosphere reacting to an attack with no visible attacker. What makes these flares so unnerving isn't just their invisibility, but their defiance of solar physics' basic rules. Flares are supposed to produce emissions across the electromagnetic spectrum, from radio waves to gamma rays. Yet ionospheric flares somehow bypass this requirement, channeling energy almost exclusively into particles that only announce themselves upon arrival. One theory suggests these events might be electron-only flares, eruptions where protons and heavier particles get left behind, creating a lopsided energy dump that slips past traditional detection methods. It's like hearing the echo of a shout without ever catching the original voice. The mystery deepens when you examine the timing. Some ionospheric disturbances precede their parent flares by minutes, as if the particles outran the light. This violates Einstein's fundamental cosmic speed limit. Nothing should travel faster than light in a vacuum. The resolution might lie in magnetic highways. Charged particles could be surfing along pre-existing field lines stretching from the Sun to Earth, taking a shortcut while light travels the long way. Observations from NASA Van Allen probes support this, having caught electrons zipping along these invisible tracks like commuters on a celestial subway. Yet even this explanation doesn't account for the flare's selective visibility. Why do some eruptions broadcast their presence across every wavelength while others hide all but their faintest traces? The answer might involve the Sun's magnetic geometry. Certain field orientations could focus particle beams into narrow jets aimed directly at Earth while suppressing telltale radiation sideways, like a flashlight pointed straight at your eyes, blinding you while leaving the room dark for everyone else. The stakes here are more than academic. Ionospheric flares may be a hidden driver of gray swan space weather events, disruptions that strike without conventional warning. In 2013, one such stealth eruption nearly blinded the Federal Aviation Administration's GPS backup systems during a critical test, despite no solar observatories reporting unusual activity. As our infrastructure grows more reliant on precise positioning and timing signals, these phantom flares could become a silent menace, throwing off power grids, navigation, and communication networks without the courtesy of a solar heads-up. Every unexplained ionospheric spike is a reminder the Sun doesn't always telegraph its punches. Some of its most potent strikes arrive without fanfare, detectable only by the ripples they leave in our fragile atmospheric shield. Until we unravel the secrets of these invisible eruptions, we're left defending against shadows reacting to solar attacks we can't even see coming. Most explosions have a clear rhythm, build up, climax, then fade. But solar flares love to break the rules. Imagine a firework that bursts twice, first a dazzling eruption, then a brief lull, and suddenly another blinding peak just when you thought the show was over. These are double-peaked flares, and they hint at something profound. The Sun's fury might operate on a hidden schedule we're only beginning to decode. The mystery lies in the timing. Typical flares follow a predictable curve. Energy spikes, plateaus, then declines as magnetic fields exhaust themselves. Double-peaked flares shatter that pattern. Observations from NASA's RESI satellite reveal these events with startling clarity. Two distinct energy surges separated by minutes or even hours, like a cosmic drummer hitting the same beat twice. What's bizarre isn't just the dual peaks, but the gap between them. A silence that suggests the Sun's engine briefly stalls before roaring back to life. One leading theory blames magnetic reconnection. Normally, reconnection, the snapping and realigning of magnetic fields, happens once during a flare. But double peaks imply the process might repeat, like a stubborn zipper that keeps reopening. High-resolution magnetograms show eerie evidence. Between peaks, new magnetic loops sometimes emerge near the eruption site, as if fresh fuel is being fed into the fire. It's possible the initial explosion destabilizes neighboring fields, setting the stage for a second act. But there's a hitch. Some double-peaked flares show no visible magnetic changes between surges, leaving physicists puzzled about where the extra energy originates. This has sparked a radical alternative, cascading acceleration, where particles gain speed in stages. The first peak might represent electrons hitting their initial energy limit, while the second comes from a delayed wave of protons reaching even higher velocities, like sprinters finishing a race at staggered intervals. The implications reach beyond theory. Double peaks often correlate with heightened radiation risks, as the second surge can catch satellites and astronauts off guard. Worse yet, these flares frequently spawn multiple coronal mass ejections, stacking space weather hazards like a 1-2 punch. If we can't predict whether a flare will single or double its fury, our early warning systems remain half-blind. Perhaps the most tantalizing clue lies in their asymmetry. In many double-peaked flares, the second burst outshines the first, suggesting stored energy we failed to measure initially. It's as if the sun plays a cosmic shell game, hiding half its power until the perfect moment. Every twin-peaked eruption whispers the same unsettling truth: our closest star still holds back its best tricks. Every explosion we've ever witnessed sends debris flying outward, except when the sun decides to rewrite the rules. Some solar flares perform a baffling reversal, their plasma surging upward into the corona like a waterfall flowing uphill. These backwards flares aren't just optical illusions, they're direct violations of how magnetic reconnection should work. When twisted field lines snap, everything should blast outward in a torrent of freed energy. Yet high-resolution footage from the Solar Dynamics Observatory shows loops of plasma defying gravity and magnetism alike, climbing into the sun's upper atmosphere with no visible force propelling them. The enigma lies in the speed and precision of these ascents. Plasma in a typical flare might reach hundreds of miles per second as it erupts. Backwards flows clock in at similar velocities, but in the opposite direction, defying the pull of the sun's colossal gravity. It's like watching a volcanic eruption where half the lava reverses midair and rockets back into the vent. Even stranger, these anomalous flows often coincide with perfectly normal outward eruptions nearby, as if the sun's physics switches rules between adjacent regions. One explanation might lie in magnetic mirrors, configurations where coronal field lines act like cosmic trampolines. If certain loops bend sharply enough, they could reflect energized particles back inward, creating the illusion of upward flow. There's just one problem: the required magnetic geometries are vanishingly rare, yet backwards flares occur surprisingly often. Another theory suggests these could be failed eruptions, where partially detached plasma gets yanked back by overbearing magnetic tension, like a slingshot pulled too tight, recoiling before release. But the most startling hypothesis: these flows might reveal unseen forces in the sun's lower atmosphere. Satellite data hints at powerful pressure waves called acoustic transients rippling beneath flare sites. These could theoretically launch material upward like a piston, overpowering both gravity and magnetic expulsion. If true, it would mean we've been blind to an entire class of solar dynamics, one where sound waves sculpt eruptions as much as magnetism does. The implications unsettle our entire understanding of stellar explosions. If flares can channel energy inward as efficiently as outward, models of coronal heating, the mystery of why the sun's outer layers are millions of degrees hotter than its surface might need revisiting. Worse yet, these reverse flows could be stealthily ferrying radiation into regions we assumed were safe, potentially reshaping how we predict solar storms. Every upward surge is a silent rebellion against our textbooks, proving the sun's fury doesn't just radiate, it ricochets. Even after a solar flare fades, its ghost lingers, not in light or heat, but in cryptic silhouettes that trace the sun's magnetic bones. These are shadow loops, faint, wispy structures that materialize in the wake of some eruptions, threading through the corona like echoes of the explosion's skeleton. They don't glow like the flare's fiery arcs. Instead, they appear as dark tendrils against the sun's bright backdrop, visible only because they absorb or deflect the ambient light passing through them. It's as if the flare leaves behind a magnetic blueprint, one that hints at energy moving in ways we never anticipated. What makes these shadows so perplexing isn't just their appearance, but their timing. They emerge after the flare's main energy release, often persisting for hours when the visible fireworks have long subsided. Observations from the Hinode spacecraft reveal something even stranger. These loops sometimes grow stronger over time, their magnetic signatures intensifying while the surrounding plasma cools. This defies the basic rule of entropy. Energy should disperse, not consolidate, in an explosion's aftermath. One theory suggests these shadows are vacuuming up residual energy from the flare, funneling it into invisible channels. Picture a sponge soaking up spilled water. Only in this case, the sponge is made of twisted magnetic fields, and the water is pure solar fury. The leading explanation points to dark reconnection, a hidden phase of magnetic reorganization where energy transfers without the usual light show. Normally, reconnection emits bright X-rays as fields snap and realign. Shadow loops might represent a quieter version of this process, like the difference between a sparking live wire and one humming with current behind insulated walls. Some researchers speculate these structures could be siphoning energy downward, feeding it back into the sun's lower layers, or even stockpiling it for future eruptions. It's a cosmic recycling program we never knew existed, yet the biggest mystery lies in their selectivity. Not all flares produce shadow loops, and those that do often follow no obvious pattern. A modest flare might leave behind intricate loop networks, while a monstrous X-class eruption vanishes without a trace. This randomness suggests an invisible threshold, some hidden condition that determines whether a flare's energy dissipates cleanly or lingers in these ghostly forms. Could these shadows be the key to predicting which eruptions will spawn secondary storms or prolonged radiation risks? For now, the loops remain solar hieroglyphics, a language of shadows we're still learning to read. Every faint strand is a clue, whispering that the sun's explosions don't truly end when the light fades. Something lingers, moving in the dark, and until we decipher its purpose, our understanding of solar flares will always be half in the shadows. The sun's explosions don't always travel alone. Some flares send mysterious echoes, secondary bursts of energy that flicker to life thousands of miles from the original eruption, like cosmic aftershocks lighting up the wrong fault line. These echo flares shouldn't exist. When a solar flare detonates, its energy should radiate outward or fade, not leap across the sun's surface to spark new fires in distant, seemingly unrelated regions. Yet time and again, satellites catch these delayed twins flaring in perfect sync with their parents, connected by some invisible thread we can't yet trace. What makes these echoes so baffling isn't just their distance, sometimes spanning further than Earth's diameter, but their timing. Unlike sympathetic flares that erupt simultaneously, echo flares follow their primaries by minutes, as if riding some slow-moving wave across the solar surface. Observations from NASA, a solar dynamics observatory, reveal an eerie pattern. The delay often matches the travel time expected for certain magnetodynamic waves, ripples moving through the sun's plasma like sound through water. But here's the catch. These waves should dissipate long before reaching echo sites, their energy spread too thin to trigger fresh eruptions. One theory suggests the sun might be hiding invisible waveguides, channels where magnetic fields funnel energy efficiently across vast distances without the usual losses. Picture shouting through a pipe instead of open air. The sound carries farther with less distortion. If certain magnetic architectures on the sun act like these cosmic pipes, they could deliver flare energy intact to distant weak spots, lighting them up like secondary fuses. There's tantalizing evidence for this. Many echo sites turn out to be regions of pre-existing magnetic instability areas primed to erupt but lacking that final push. But there's a darker possibility. Some echo flares exhibit energy outputs that dwarf what any wave could reasonably deliver. This has led a minority of researchers to propose a radical alternative: magnetic entanglement, where distant points on the sun's surface might be quantum-linked, sharing energy through mechanisms we've only glimpsed in laboratory experiments. While controversial, this idea gains traction from odd coincidences like echoes mirroring their parent flares, exact spectral signatures despite the vast separation. The stakes of solving this riddle extend beyond astrophysics. Echo flares often coincide with complex space weather events where multiple eruptions strike Earth in quick succession. If we're missing these hidden connections between flares, our ability to predict solar storms remains dangerously incomplete. Every echoing burst is a reminder the sun's explosions don't exist in isolation. They're part of a hidden conversation, one we're only beginning to overhear. Gamma-ray bursts from solar flares are supposed to be fleeting, violent flashes that vanish as quickly as they appear. But the sun has a habit of leaving behind ghosts. Long after some flares fade, faint gamma-ray emissions linger like cosmic afterglows, defying every expectation of how particle acceleration should work. These aren't just fading echoes, they're persistent signatures of energy that refuse to dissipate, hinting at processes operating in the shadows of solar physics. The mystery begins with the timeline. Gamma rays are born when particles, usually protons, collide at extreme speeds, a process that should cease once a flare's magnetic engines shut down. Yet satellites like NASA's Fermi Gamma Ray Space Telescope keep picking up signals hours after the main event, sometimes with energy levels comparable to the flare's peak. It's like turning off a light switch only to find the bulb still glowing dimly, powered by some hidden reserve. The most baffling case occurred in September 2017, when gamma rays from a modest M-class flare persisted for nearly 12 hours, their spectral fingerprints identical to the initial burst. Where was this energy hiding, and why did it leak out so slowly? One clue lies in the ray's erratic pulsations. Unlike the steady decline of most post-flare emissions, these gamma ghosts often flicker, flaring and fading in a regular burst. This suggests trapped particles might be bouncing between magnetic structures, gradually escaping like water leaking through cracks in a dam. High-resolution magnetograms reveal something startling. Many lingering gamma events correlate with closed magnetic loops, regions where field lines curve back onto themselves, creating natural prisons for high-energy particles. Under the right conditions, these loops might act like cosmic accelerators on standby, squeezing extra collisions from protons long after the central explosion ends. But there's a wrinkle. Some ghostly emissions originate far from the flare site, in regions with no apparent magnetic connection to the original eruption. This has led to a radical idea. What if the sun's entire corona serves as a particle reservoir? Turbulent plasma waves crisscrossing the sun's atmosphere could keep protons agitated for hours, turning the corona into a diffuse gamma-ray factory. Imagine shaking a snow globe and watching the flakes swirl. The flare might be the initial shake, but the particles keep colliding in the unsettled aftermath. The implications rewrite solar risk assessments. Lingering gamma radiation means satellites and astronauts could face extended exposure even after a flare seems over. Worse yet, these ghosts might signal hidden particle buildups that could trigger secondary eruptions. Every unexplained afterglow is a reminder. When the sun explodes, the fireworks don't always end when we think they should. Some part of the show continues unseen, rewriting the rules of cosmic physics one gamma ray at a time. Most solar flares scream their arrival across every wavelength except when they don't. Hidden among the sun's explosive repertoire are silent flares, eruptions that barely whisper in X-rays or radio waves yet unleash torrents of high-energy particles toward Earth. These stealthy events slip past our early warning systems like cosmic ninjas, detectable only when their particle payloads slam into our planet's magnetic field. In February 2022, researchers at the University of New Hampshire documented one such event, a flare so quiet it barely registered on solar monitors, but whose proton storm lit up detectors across 5 satellites. The discrepancy was staggering. Electromagnetic energy output 1,000th of a typical flare, yet particle acceleration rivaling eruptions 10 times stronger. The mystery lies in the disconnect between light and matter. Standard flare physics dictates that particle acceleration, the process that whips electrons and protons to near light speeds, should produce telltale electromagnetic signatures. As charged particles spiral along magnetic field lines, they should emit radio waves and X-rays like cosmic lighthouses. Silent flares break this chain reaction, accelerating particles with eerie efficiency while scarcely lighting up the usual electromagnetic channels. It's like watching a fireworks factory explode without the flashes or booms, just shrapnel raining down miles away. One groundbreaking theory suggests these flares might operate as dark accelerators. Instead of the chaotic, wide-scale magnetic reconnection that powers typical eruptions, silent flares could rely on ultra-focused particle beams channeled through pre-existing magnetic tunnels. Picture a particle collider built into the sun's atmosphere, where magnetic fields act like precision rails, guiding particles to extreme energies with minimal energy wasted on visible fireworks. Observations from the Parker Solar Probe support this, having detected narrow particle streams emerging from otherwise calm regions of the sun, as if invisible guns were firing charged bullets from hidden ports. The consequences for space weather forecasting are profound. Silent flares could represent a whole class of blind spot eruptions that bypass our current detection networks. While we obsessively monitor X-ray and ultraviolet emissions as flare indicators, these stealth events might be slipping through, their particle storms arriving unannounced. The 2022 event, for instance, delivered enough radiation to have threatened astronauts in lunar orbit, all without triggering standard solar alerts. Perhaps the most unsettling implication is that silent flares could be rewriting the rules of particle acceleration itself. Some models now suggest the quietest eruptions might be the most efficient at producing high-energy particles, turning our understanding of energy conversion upside down. Every undetected proton surge is a quiet challenge to our solar monitoring paradigm's proof that the sun still knows how to catch us off guard, not with a roar, but with a whisper that carries hidden barbs. Imagine a spaghetti bowl of magnetic fields, twisted tighter than a corkscrew and knotted into impossible tangles. That's the heart of the magnetic knot theory, a bold idea that suggests some of the sun's most bizarre flares might be powered by structures so complex they defy our current physics. These hypothetical knots aren't just messy, they're cosmic pressure cookers storing insane amounts of energy in loops and braids that could snap with the right trigger. And if they exist, they might hold the key to explaining everything from zombie flares to those mysterious gamma-ray afterglows. The theory hinges on a simple but radical premise. The sun's magnetic fields might twist far beyond what we've observed. Standard models assume fields reconnect when they're moderately tangled like phone cords twisted a few times. But what if some regions coil into intricate, self-reinforcing knots, where every loop tightens another? Simulations at laboratories like the University of Oslo show these structures could theoretically store up to 100 times more energy than smooth fields, releasing it in erratic bursts when the knots finally unravel. Picture a knotted rope fraying strand by strand instead of snapping cleanly. Each break could fuel a mini flare or delay an eruption for hours. Evidence for this hides in the sun's most baffling flares. Take those ultra-long duration flares we discussed earlier, the ones that burn for days. Knot theory suggests they might not be single explosions, but slow-motion unspoolings of colossal magnetic tangles. High-resolution magnetograms occasionally catch hints of these structures, regions where field lines writhe like snakes in a basket, too jumbled for current imaging to fully map. And those helical flares, the ones that twist like DNA, they could be visible manifestations of knots finally bursting free, their coiled shape echoing the hidden chaos beneath. But here's the catch: no one's ever definitively observed a magnetic knot. The sun's atmosphere is too opaque and our instruments too limited to peer deep enough. Some researchers argue these structures might be mathematical ghosts, artifacts of oversimplified simulations rather than real solar phenomena. Others point to lab experiments where knotted plasma spontaneously untangles too quickly to match flare timelines. The most damning counterargument: even if knots exist, they'd be so unstable that the sun's turbulent surface should shred them before they could store significant energy. Yet the theory refuses to die because it solves puzzles nothing else can. Those cold flares with inexplicable thermal voids. A tightly knotted region might redirect heat along hidden channels, leaving pockets unnaturally chilled. Sympathetic flares erupting continents apart. Knots could stretch across vast distances, transferring energy invisibly before detonating multiple sites at once. Even the missing neutrino problem gets a potential answer. If flares draw energy from magnetic knots rather than nuclear processes, the lack of expected particles suddenly makes sense. The quest to prove or debunk this idea is driving some of solar physics' most ambitious missions. NASA's upcoming MUSE mission aims to hunt for knotted fields with unprecedented resolution, while advanced algorithms scour decades-old flare data for subtle magnetic footprints. Whatever the outcome, the magnetic knot theory has already reshaped how we see the sun. Not as a placid ball of plasma, but as a cosmic macrame project gone wild, where every tangle could hide the seeds of the next great explosion. Until we crack this enigma, the sun's most twisted secrets remain just out of reach, knotted up in layers of theory and wonder. The sun isn't just erupting, it's performing. Among its most mesmerizing acts are dancing flares, eruptions where the point of energy release doesn't stay put but skitters across the solar surface like a cosmic wildfire changing direction mid-burn. These aren't just random movements, they're rapid, purposeful traverses that defy the stability we expect from magnetic explosions. Imagine a fireworks display where the sparks don't shoot upward but zigzag sideways at speeds exceeding 1,000,000 miles per hour, leaving physicists scrambling to explain how energy can relocate so fluidly in what should be a chaotic but anchored explosion. What makes these flares so baffling is their precision. Standard models assume reconnection. The snapping and realigning of magnetic fields that powers flares happens in localized stationary sites. But dancing flares laugh at that assumption. Observations from NASA's Solar Dynamics Observatory reveal bright X-ray kernels, the flare's energy heart, sliding along magnetic channels faster than a bullet, sometimes covering distances greater than Earth's diameter in under 10 minutes. It's as if the flare's engine is mounted on rails, rocketing through the sun's atmosphere with eerie directional control. One clue lies in the sun's hidden magnetic highways. High-resolution magnetograms show these flares often follow pre-existing filament channels, invisible threads of concentrated magnetic flux weaving beneath the surface. Think of them as cosmic pipelines capable of channeling energy like water through a hose. When reconnection ignites at one point, the explosion might not just dissipate, it could race along these channels, lighting up successive segments like a fuse burning toward dynamite. Yet even this explanation hits a snag. Some dancing flares abruptly change course, doubling back or branching onto paths that magnetograms swear shouldn't exist. The leading theory blames magnetic slippage, a phenomenon where reconnection doesn't just release energy but actively reconfigures the surrounding fields mid-eruption. Picture a zipper that not only unfastens but sews new teeth as it moves, constantly altering the landscape it travels through. Simulations from the University of Helsinki suggest this could create a domino effect. Each reconnection event warps nearby fields, creating fresh instability that pulls the flare's focus outward in unpredictable leaps. But the most startling implication, dancing flares might be rewriting the rules of energy transfer itself. their movement often correlates with extreme particle acceleration, far beyond what stationary models predict. This hints that the flares aren't just relocating, they're amplifying as they go, tapping into hidden reserves of energy like a snowball rolling downhill and gathering mass. If true, our whole framework for predicting flare intensity may need overhauling. A flare that starts modestly could escalate catastrophically simply by traversing the wrong magnetic terrain. For now, these nomadic explosions remain one of solar physics' most captivating puzzles. Every skittering flare is a reminder. The sun doesn't just explode, it choreographs its violence, dancing to a rhythm we're only beginning to hear. And until we decode the steps, our models will keep stumbling to keep up. When solar flares erupt, they should toss enormous amounts of material into space calculated down to the last ton of superheated plasma. Yet something strange keeps happening. The numbers don't add up. Careful measurements show that some flares lose significantly more mass than what's visible in their ejections. It's as if part of the eruption vanishes into thin air, leaving physicists hunting for solar ghosts. This missing mass problem isn't just a bookkeeping error. It hints at a hidden layer of solar activity where plasma might be escaping through backdoors we can't yet see. The discrepancy first came to light in 2018 when researchers analyzing data from NAS, a solar and heliospheric observatory, noticed something off about a powerful X-class flare. The eruption's energy release suggested it should have blasted roughly 10 billion tons of plasma into space, yet coronagraph images revealed barely half that amount visibly departing. At first, scientists assumed instrumentation errors or overlooked plasma streams. But as similar mismatches piled up across dozens of flares, a disturbing pattern emerged. The sun might be stealthily ejecting mass in forms our telescopes can't catch. One leading theory blames dark plasma, ejections so diffuse or cool they evade standard detection. Most coronagraphs spot flares by looking for sunlight scattering off electrons in hot plasma. But if some material gets expelled at unusually low temperatures or in electrically neutral clumps, it could slip through observational nets like smoke through a sieve. There's tantalizing indirect evidence. Certain flares produce odd magnetic field disturbances far from the eruption site, as if unseen mass is warping space as it moves. The European Space Agency's solar orbiter recently spotted one such anomaly, a magnetic ripple traveling ahead of a visible coronal mass ejection, possibly heralding an invisible vanguard. Another possibility cuts deeper. The missing mass might not have left at all. It could be falling back into the sun through those mysterious downflows we discussed earlier. High-resolution spectra reveal faint traces of heavy elements like iron sinking at incredible speeds post-flare, hinting at a brutal recycling process. Picture a fountain where some water arcs outward while the rest drains straight back down the pipes. If enough material gets sucked back in before our instruments can tally it, the math would always come up short. The most radical explanation: we might be misjudging the sun's mass balance entirely. Certain plasma physics models suggest flares could briefly warp local spacetime, making ejected material appear lighter or slower than it truly is, a gravitational illusion akin to Einstein's bending starlight. While controversial, this idea gains traction from gamma-ray flares exhibiting similar energy-mass mismatches, as if the sun's explosions occasionally dabble in relativity. The stakes here extend beyond astrophysics. Missing mass could mean missing threats, stealthy plasma clouds arriving at Earth without the usual warning signs. In 2021, a minor flare triggered unexpectedly severe geomagnetic disturbances. Later analysis suggested an undetected mass ejection might have ridden ahead of the visible storm. Every ton of unaccounted-for plasma is a wild card in space weather forecasting, potentially carrying enough momentum to knock satellites off course or amplify radiation belts. Perhaps the humbling truth is that solar flares don't just eject matter, they transform it. Between invisible outflows, swallowed returns, and physics we've yet to decipher, the sun's ledgers will never balance easily. Each eruption isn't just a release of energy, but a reminder when it comes to the cosmos, what we can't see still shapes everything. Some of the sun's most bizarre performances don't involve explosions at all, just sudden appearances and disappearances that leave astronomers questioning their eyes. Imagine tracing a flare's magnetic skeleton, only to watch certain structures blink in and out of existence like cosmic magic tricks. These are the phantom loops, magnetic arches that materialize during eruptions without warning, linger just long enough to be documented, then vanish without obeying the usual laws of plasma decay. High-resolution footage from the Solar Dynamics Observatory captures these ghosts in unsettling detail. A normal coronal loop glows for hours as heated plasma spirals along magnetic field lines. Think of molten iron flowing through a glass pipe. Phantom loops break all the rules. They flash into visibility during flares, sometimes forming perfect semicircles spanning 20 Earths, then dissolve within minutes as if someone flipped a switch. The strangest part, their disappearance doesn't follow the expected cooling curves. They don't fade gradually like dying embers. One moment they're there, conducting plasma at 1,000,000 degrees, the next, they're simply gone, leaving no trace in ultraviolet or X-ray wavelengths. The leading theory suggests these loops might be projections, magnetic structures that aren't physically filled with plasma until some hidden trigger floods them. Picture an empty highway suddenly packed with cars for 30 seconds before clearing just as abruptly. Observations from the European Space Agency's Solar Orbiter reveal eerie supporting evidence. Phantom loops often coincide with bursts of radiostatic, as if invisible forces are briefly tuning magnetic channels to attract plasma. But what's tuning them? Some researchers point to Alfvén pulses, hypothetical magnetic shockwaves that could temporarily illuminate field lines like a strobe light hitting a spider web. Yet the deepest mystery lies in their timing. Phantom loops disproportionately appear during flares exhibiting other anomalies, gamma-ray excesses, particle acceleration bursts, or those puzzling downward plasma flows. This has led to a radical idea. These apparitions might be side effects of energy transferring between different layers of the sun's atmosphere through mechanisms we can't directly observe. When a flare dumps energy into the corona, some fraction might briefly light up magnetic pathways that normally stay dark, revealing a hidden circulatory system we never knew existed. The implications rewrite how we map solar energy flow. If phantom loops trace secret magnetic connections, they could explain how certain flares influence distant regions or why some eruptions seem to recharge mysteriously. Every vanishing act is a clue the sun isn't just showing us its explosions, but occasionally flashing glimpses of the invisible architecture behind them. And just like any good magic trick, the real wonder isn't in what disappears, but in what these fleeting visions reveal about the mechanisms hidden in plain sight. Atomic fingerprints don't lie except when the sun decides to rewrite the rules. Every element in a solar flare leaves a telltale signature in the form of spectral lines, bright or dark marks in the light spectrum that reveal temperature, density, and composition. But during some eruptions, these lines start behaving like mischievous ghosts. Iron emissions that should blaze brightly at 1,000,000 degrees suddenly go dark. Calcium lines flicker where they should hold steady. These aren't just observational glitches, they're full-blown rebellions against quantum physics, making it impossible to trust even our most basic measurements of the sun's fury. The puzzle centers on something called non-thermal line broadening, where spectral lines smear unpredictably during flares. Normally, a hot gas produces sharp lines. Think of a barcode with clean, distinct stripes. But under the sun's extreme conditions, some lines widen into fuzzy bands, as if the atoms themselves can't decide what energy they're emitting. This blurring isn't random. Observations from the interface region imaging spectrograph iris show it happens most dramatically in elements like silicon and magnesium, often at the precise moment a flare's core reaches peak intensity. It's like the sun scribbling over its own barcode, erasing the very data we need to decode its explosions. One theory blames turbulent soup plasma conditions. As magnetic fields tear apart during a flare, they might churn the surrounding gas into a froth of microscopic whirlpools, each one Doppler shifting light slightly differently. The result, a spectral traffic jam where overlapping shifts blur the lines into oblivion. There's just one problem. Advanced simulations show this turbulence shouldn't persist long enough to match the observed smearing. The lines stay fuzzy far longer than the models allow, as if some hidden force keeps stirring the pot even after the flare's main chaos subsides. A wilder idea suggests we're seeing quantum effects play out on macroscopic scales. Under normal conditions, atoms emit and absorb light at specific, predictable wavelengths. But in flares, the sheer density of free electrons might be pressure-broadening spectral lines, a phenomenon usually seen in dense stellar cores, not the relatively thin solar corona. Imagine a packed elevator where everyone's jostling alters their voices. Similarly, crammed electrons could distort the light emitted by ions, smearing the expected signals. Recent measurements from the Daniel K. Inau Solar Telescope hint at this, showing spectral distortions that align better with extreme density models than traditional turbulence. Yet the most unsettling anomalies involve lines that vanish entirely. During a massive flare in 2021, NASA's Extreme Ultraviolet Variability experiment watched as iron-24 emission, typically a reliable temperature gauge, completely disappeared for 7 minutes, only to snap back like a flipped switch. This wasn't just blurring, it was a total breakdown in the atomic rulebook. The leading explanation: the flare's particle beams might have temporarily ionized the iron atoms into higher states, effectively silencing their spectral voices. If true, it means flares could be selectively erasing their own diagnostic clues, like criminals wiping fingerprints mid-crime. The consequences ripple far beyond academia. Spectral lines are the backbone of solar monitoring, the vital signs we use to gauge flare intensity and predict space weather impacts. If these signatures can't be trusted, our early warning systems might be missing critical cues. A misread temperature spike could mean underestimating radiation risks to satellites or overestimating a coronal mass ejection speed. Every anomalous line is both a challenge and an invitation. The sun isn't just breaking its own rules, but daring us to discover the new ones it's writing in real time. And until we crack this code, our understanding of solar flares will always be slightly out of focus. Most explosions build to a crescendo, except on the sun, where some flares skip the warm-up entirely. Imagine a light switch flipping from off to blinding in less time than it takes to blink. These are the solar system's drag racers flares that erupt at full fury in mere seconds, leaving our best predictive models choking on their cosmic dust. Theoretical physics says these explosions should take minutes to ramp up as magnetic fields tangle and snap. But when the sun decides to break its own rules, it doesn't just bend them, it shatters them with a speed that defies logic. Take the flare of May 3, 2022. NASA's Solar Dynamics Observatory caught the entire event in brutal detail. 0 to X-class in 4.3 seconds, a burst of energy so sudden it looked like a film missing frames. The temperature curve was even more baffling, plasma rocketing from 10,000 to 10 million degrees in less time than a human heartbeat. Standard reconnection models, which predict a gradual energy release as fields reorganize, simply can't explain this kind of violence. It's the difference between a gasoline fire and a detonation. Both release energy, but one does it faster than physics should allow. So where's the cosmic loophole? One theory points to pre-stressed magnetic field structures already wound to breaking point before the flare even begins. Picture a rubber band stretched taut by invisible hands, needing just the slightest nudge to snap. High-resolution magnetograms reveal eerie supporting evidence. Certain fast and furious flares erupt from regions where the magnetic gradient is already steeper than physics textbooks deem stable. The sun, it seems, keeps a pantry of preloaded explosions ready to unleash at a moment's notice. But speed isn't the only anomaly. These flares often punch above their weight, producing more X-rays and energetic particles than their slower counterparts with similar magnetic measurements. This has led to a radical idea. Maybe the energy isn't coming from reconnection alone. Some researchers speculate these ultra-fast eruptions might tap into the sun's acoustic waves, vibrations normally associated with sound propagation, converting their kinetic energy directly into heat through a process we've yet to fully model. Imagine a singer shattering glass with a high note, only here that note is the sun's own seismic roar, channeled into a magnetic lightning strike. The implications are staggering. If we're underestimating how quickly flares can escalate, our early warning systems for satellite operators and astronauts might be fatally flawed. A moderate flare that suddenly leaps to X-class intensity could bathe Earth's orbit in lethal radiation before alerts even finish processing. Worse yet, these rapid flares frequently correlate with the most geo-effective coronal mass ejections, the kind that blindsided Quebec's power grid in 1989. Every ultra-fast eruption is a ticking clock, reminding us that the sun's violence operates on timescales we're only beginning to measure, let alone understand. Perhaps the most unsettling truth, for all their fury, these flares might be the sun's way of showing off. In a universe where stars routinely take billions of years to evolve, ours has mastered the art of the millisecond explosion, a reminder that even the most familiar cosmic objects still hold surprises in reserve. The next time a flare explodes faster than thought possible, remember, it's not breaking the rules, it's revealing how many we've yet to discover. The sun's poles are a lawless frontier, where flares don't just break the rules, they rewrite them. At the equator, solar explosions follow familiar patterns. Twisted magnetic fields snap, plasma erupts, and radiation floods outward. But near the poles, flares dance to a different rhythm. They last longer, they spark in unexpected places, and sometimes they vanish without the usual aftermath, leaving scientists staring at data that refuses to make sense. One of the most glaring oddities is their endurance. Polar flares often outlive their equatorial cousins by hours, burning with a stubborn persistence that defies decay models. A typical mid-latitude flare might rage for 15 minutes before fading, while its polar counterpart lingers like a campfire in Arctic wind, its energy source mysteriously replenished. The European Space Agency's solar orbiter caught one such anomaly in 2020, a modest C-class flare near the sun's north pole that flickered for nearly 8 hours, its magnetic loops refusing to fully dissipate. The culprit, theorists suspect the sun's polar magnetic fields, which weave into bizarre configurations unlike anywhere else on the star. At the poles, the sun's global magnetic lines converge like tangled yarn, creating structures that might trap and recycle energy rather than releasing it all at once. Then there's the strangeness of their birthplaces. Most flares erupt from sunspots, dark, magnetically hyperactive blemishes that pepper the sun's middle latitudes. But polar flares often ignite in seemingly empty zones where magnetograms show only faint, disorganized fields. It's like watching a forest fire spark in the middle of a frozen lake. Some researchers propose these eruptions tap into submerged magnetic rivers currents flowing deep beneath the surface, invisible to our telescopes until they suddenly pierce through near the poles. Others argue the polar environment itself is the key. With the sun's rotation slower at the poles, magnetic fields might twist tighter before snapping, like a corkscrew wound to its breaking point. But the deepest mystery lies in what these flares don't do. Equatorial flares usually trigger cascading effect shockwaves that ripple through the corona or particle storms racing toward Earth. Polar flares, by contrast, often leave the surrounding plasma eerily undisturbed. Data from NASA's Parker Solar Probe reveals something startling. Even powerful polar eruptions frequently fail to produce the high-energy particle streams that define flares elsewhere. It's as if the poles absorb their own shock, silencing explosions that would echo across the solar system if they happened closer to the equator. The implications could rewrite solar weather forecasting. If polar flares operate by fundamentally different physics, we might be underestimating their potential to disrupt satellites or power grids. A recent study found that particles from polar events sometimes take unexpected paths, spiraling along the sun's global magnetic field to strike Earth from angles our early warning systems don't monitor. And with Solar Orbiter now venturing closer to the poles than any probe before, each new observation peels back another layer of this enigma, revealing a side of the sun where familiar laws bend, and flares play by rules we're only beginning to decipher. Perhaps the most humbling realization: the sun isn't one uniform sphere but a mosaic of extremes. What we've learned from equatorial flares might just be the first chapter of a far stranger story. And at the poles, where magnetic fields knot into shapes we can't yet map, the sun keeps its most bewildering explosions waiting just out of view. Just when you think a solar flare has spent its fury, the sun delivers one last surprise: a sudden, brilliant flash of light in the dying moments of the eruption. This eerie phenomenon, dubbed the final flash, defies every expectation of how flares should end. Scientists expected the sun's explosions to fade quietly as their magnetic fuel burns out, like embers cooling after a fire. But instead, some flares roar back to life in their final seconds with a burst of energy so intense it can outshine the flare's original peak. It's as if the sun has a hidden pocket of energy it saves for a dramatic exit, and no one knows where it's coming from. The mystery lies in the timing. Final flashes don't happen randomly, they strike when the flare seems all but finished, often after minutes or even hours of steady decline. Observations from Japan's Hinode satellite captured one such event in 2019, where an X-class flare dimmed to near invisibility in ultraviolet light, only to blaze back with 70% of its original brightness in under 12 seconds. Even stranger, these late surges often emit light at different wavelengths than the main flare, suggesting a completely separate energy source kicking in at the 11th hour. One theory points to the sun's deeper layers as the culprit. While flares typically draw energy from twisted magnetic fields in the corona, their final flashes might tap into reservoirs buried beneath the surface, vast stores of energy normally locked away by the sun's churning plasma. Imagine a pipeline bursting underground long after the initial explosion above has settled. High-resolution heliosismology, the study of solar sound waves, has detected strange vibrations coinciding with these flashes, hinting at disturbances far below the visible eruption site. But there's a wrinkle. Some final flashes occur without any corresponding seismic activity, implying another mechanism might be at play. An alternative explanation suggests these bursts could be caused by magnetic echoes, energy trapped in closed loops that finally finds an escape route as the flare's structure collapses. Picture a room of mirrors shattering in sequence, each reflection releasing another wave of light. Data from NASA's Solar Dynamics Observatory supports this, showing final flashes often erupt where collapsing magnetic arcs intersect with stable ones, like frayed wires sparking as they're pulled apart. The implications ripple through solar forecasting. If flares can summon hidden energy reserves without warning, our models for predicting radiation risks and satellite disruptions might be missing a critical variable. A seemingly spent flare could suddenly unleash a fresh wave of X-rays or particles just as operators let their guard down. Worse yet, these flashes might help explain rare zombie flares that resurrect hours after appearing dead. Could the final flash be the first glimpse of a larger, more persistent energy source we've overlooked? The sun has always played by its own rules, but these last-second surprises feel like deliberate taunts, a cosmic magician saving its best trick for the encore. Until we uncover what fuels these final acts, every fading flare leaves us waiting for the other shoe to drop, wondering if the explosion is truly over or just pausing to take a bow. From vanishing flares to gamma-ray ghosts, from dancing firestorms to silent eruptions that strike without warning, we've journeyed through 30 of the sun's most bewildering acts of defiance. Each one a reminder that our closest star, the very heartbeat of our solar system, remains a master of illusion, hiding more than it reveals. Just when we think we've cracked its code, the sun throws another curveball. Zombie flares that refuse to die, phantom loops that vanish into thin air, or polar explosions that laugh at the rulebook. The sheer breadth of these enigmas is humbling. We're not just missing pieces of the puzzle, we're still figuring out how many pieces there are. Consider what this means for science itself. Every unexplained phenomenon we've explored isn't just a gap in knowledge, it's an open door. A chance to rewrite textbooks, to invent new instruments, to see the universe with fresh eyes. The sun's mysteries have already revolutionized physics, magnetic reconnection, particle acceleration, plasma turbulence, all concepts born from trying to decode these solar riddles. Who knows what breakthroughs might come next? Perhaps the key to fusion energy hides in those supersonic downflows. Maybe the secret to predicting space weather lurks in the whispers of ionospheric flares. Or could those missing neutrinos hint at entirely new physics waiting to be uncovered? Here's the beautiful truth: the sun wants to be understood. Every flare it launches, every particle storm it hurls our way is a data point, a clue wrapped in fire. With missions like Parker Solar Probe diving into the sun's corona and the upcoming European Solar Telescope peering deeper than ever, we're on the verge of revelations that could redefine our relationship with this cosmic powerhouse. But progress doesn't just happen in labs or launch pads. It starts with curiosity, with questions, with moments like right now when someone watching this thinks, "Wait, how does that work?" and falls down the rabbit hole of discovery. So keep wondering, keep questioning, because the sun isn't done surprising us, and neither is the universe. If this journey through solar mysteries lit a spark of fascination, hit that subscribe button. We've got plenty more cosmic conundrums to explore together. And drop a comment below. Which of these 30 phenomena blew your mind the most? Was it the flares that burn colder than they should, or the ones that dance across the sun like cosmic wildfire? Let's keep the conversation blazing. After all, the next great solar mystery or its solution might come from you.